Alright guys, these examples will help guide you through some practice before your Unit 2 Practice 2 assignment. And the first thing we want to do is really get around the idea of explanatory and response variables. So one key thing to remember, we know that the explanatory is the x variable, and it goes on the x-axis, explanatory, x-axis. Your response is the y. But another thing that's going to help you out is the explanatory is the thing that's doing the predicting. Okay, so we would call it oftentimes the predictor. So think about what it is that is doing the predicting in each scenario, and let's do that. For each of these examples 1 through 3, we want to identify what is the explanatory and what is the response. So let's go ahead and label them. Kelly wants to know if she can predict a student's weight from his or her height. She wants to predict a student's weight from their height. So the predictor, the thing that's doing the predicting, is the height. Thus, that is our response variable. Now, what is it she's trying to predict? The thing that she is trying to predict is the weight. So that is what we are trying to predict. That's our response variable. Now, you might think like, wait, shouldn't I be able to also predict their weight or predict their height from their weight? And the answer is yeah, probably. Interestingly, it doesn't really matter which one is your x or y axis mathematically, which one is your explanatory response variable. That's all really being described in the context of your study. That's what's important. So explanatory response variable, not important mathematically, but it is important for the context of the study, and we'll see why that is a little bit later on. Now, how does drinking beer affect the level of alcohol in people's blood? I see a couple of key things here. Affect, right? One thing is affecting a change in another. So one thing is changing another. The explanatory is doing the changing. The response is getting changed. Okay? So in a study of adult volunteers that drank different numbers of cans of beer, 30 minutes later a police officer measured their blood alcohol levels. Identify the explanatory and response variables. Okay? So what was doing the predicting? What was explaining the change in something? Well, the amount of beer was the cause of some kind of change in the blood alcohol level. So, in the context of this experiment, we said that the number of cans of beer, that's going to be our explanatory variable. And our response is going to be what? What actually changed? Their blood alcohol levels. The blood alcohol levels are going to be the response variables. Okay. Number 3, National Student Loan Survey provides data on the amount of debt for recent college graduates and how stressed they feel about college debt. Sociologist looks at the data with the goal of using amount of debt to explain the stress caused by college debt. So what's doing the explaining? Amount of debt. That's doing the explaining. Whereas the response, what is changing because of that amount of debt, or maybe not because of, but in relation to, it is stress. And there we have it. So that explains explanatory and response variables very succinctly. Let's go ahead now and try to take a look at making some scatter plots and describing what we see, the correlation between those two things. Alright, so example number 4, making and describing a scatter plot. Here we're going to actually plot those points. We're going to try and describe that relationship. Are these two variables correlated to each other? Does one help explain a change in the other? That's what we want to know. So each member of a small statistics class ran a 40-yard dash and then did a long jump with running start. The table below shows the sprint time in seconds and the long jump distances. Okay? We want to make a scatter plot to show the relationship between sprint time and long jump distance. Okay, and then we're going to describe what you see, the strength, direction, form, and anything unusual, all those things that we're supposed to describe when we're looking at quantitative bivariate data. So the first thing that we want to think about is what's going to be on the x-axis. What are we going to put here? What is doing the explaining? Well, to me, I think it makes sense that if you can run faster, you can jump farther. So to me, I would say the sprint time is going to be the x-axis. The sprint time is going to help explain the long jump distance. Okay, so what I want to do when I'm on here and I'm writing this out, on the x-axis, I will go ahead and put sprint time, and I will write it in seconds, and then the long jump distance on the y-axis, and we'll do that distance in inches. Now, before I start marking things off, I want to see what's my minimum and what's my maximum. Okay, so my minimum for the shortest sprint time, it looks like is maybe 5.05 seconds. That might have been the fastest. 5.05 seconds, that was my min. And then the longest or the slowest sprint time looks like it was 7.25 seconds. That was the slowest. Okay, so I want to go from 5.05 to 7.25. Now, remember that I said before we might want to do a broken line on the x-axis. In our lecture video, I mentioned that we might want to do this because that's wasted space to count from 0 all the way up to 7. We don't need to do that, okay? And we can actually just go ahead and plot that first one here at 5, and then maybe we'll go by 0.5 seconds. 0.5, 6, 0.5, 7, and then 7.5. Okay? Again, we're just kind of like looking to eyeball things right now. We're getting a rough idea. So 5, 6, and 7 seconds. Now, on the y-axis, what's the shortest long jump distance? Our shortest long jump distance, it looks like it was 65 inches, while the longest was about 3 times that, almost 184 inches. So again, we've got a ton of wasted space, and the vertical distance, like each one of these isn't going all the way up from 0. That's not what we really are caring about. We are looking at the relationship between the x and y value, not just the starting point, the x-axis, and all the way up to its height of the y value. So we can actually use a broken line for quantitative data and scatter plots, and we'll do that here too. So we'll use a broken line on the y-axis as well, and I want to start at maybe, I don't know, we can start at 50, and then maybe we can count by 50s to go all the way up to 100, or to 200. So 50, 100, 150, 200. Okay, and you again might say, oh, there's still a lot of wasted space. If you want to, you can stretch that out, and maybe we can do that. 100, 150, 200. You can even start to make your middle tick marks just to help you kind of divide things up a little bit more too. And now we've got our scale. Okay, so that's usually the most difficult thing, is just setting the right scale. And there's not necessarily one right or wrong way to do it. You just want to do it in a way that's going to be easy to read and efficient for you. Now, you can also use different websites, like alcula.com has a really handy website for you to be able, or has a really handy 2-variable calculator that can make scatter plots of quantitative data. Excel, Google Sheets, you can find ways to make scatter plots for you digitally, and that will help out a lot too. So now I'm going to go and just start plotting these points one by one, starting with 5.41, comma 171. So 5.41 is going to be somewhere like right over here on the x-axis, but then it's going to go all the way up to 171, so that's going to be roughly right about here. And when we are sketching a scatter plot, you don't need to be super precise when you're setting your own scale. If you're provided a scale, that's when you need to be a little bit more deliberate. Next one, we have 5.05, 184, so that's going to be just to the right of 5 seconds, and then it's going to be a little bit closer to 200. It's going to be right about here. Okay, so now we'll go through and just start doing these rather quickly. Alright, so there's our scatter plot of each of our different individuals. Remember, each individual got an x and y coordinate point corresponding to their sprint time in seconds and long jump distance in inches. Now we just need to describe what we see. Well, the first thing I see is that, yeah, this kind of does form a linear pattern. If I were to draw some kind of shape that went through most of those data points, it looks like it would be a line. So I would say that's pretty obviously a line. Now, how close are these dots to the line? I would say those are fairly close, right? I would say it's not perfect, but I would say it's at least moderately strong, right? They're very close. They're pretty close to that line. It seems like I would pretty reliably be able to predict somebody's long jump distance in inches if I know how fast they can run the 40-yard dash. Okay? It seems to be at least pretty consistent. Now, what direction is it going? It's going down and to the right. Down and to the right would mean a negative slope, so this is going in the negative direction. Okay? So, that's all we need to do is just put this all together in one sentence. There is a moderately strong negative linear relationship between sprint time and long jump distance. Let's write it out. That's really all you need to say. Now, what you can tell with this is that since there is a pretty obvious relationship, try to describe it. As sprint time increases, the long jump distance decreases. What does that also tell you? Seems to me like they are associated with each other, right? As one's sprint time increases, their long jump distance decreases. You could also say it the other way. As one's sprint time decreases, the long jump distance increases. If they run faster, they jump farther. So that seems to make quite a bit of sense. Now, let's take a look at another one that might be a little bit more tricky as far as trying to interpret what we see. And it'll show you the lengths at which we can actually start to make connections with data and how it connects to real world applicable stuff. Our next example is going to look at McDonald's salads where we're comparing their sodium and fat. So the table below lists 10 different salads along with the amount of sodium in milligrams and the amount of fat in grams. So this is maybe a little bit outdated, but what we're going to want to do is make a scatter plot and describe what we see, right? We want to describe the strength, the direction, the form, and the anything unusual, which might include big gaps or big clusters or any unusual influential points potentially or anything like that, okay? So with this, what we are going to want to start to think about is which one should be our explanatory and response variable. Is sodium going to explain fat, or is fat going to explain sodium? And to be honest, I don't know. And again, it actually won't matter. So I challenge you to go ahead and try and make this on your own, and you choose. And we are going to start to see, I want you to compare what you have to mine. Okay, I'm going to go ahead and use fat as my explanatory variable and my sodium as my response. Now again, if you want to see how it looks a little bit different by just changing those two things, you'll notice that the description is not going to change. So I challenge you to go ahead and try and flip them. Try to do your X as your sodium and your Y as your fat and see how we differ. Okay? Pause the video now if you need to. Otherwise, I'm going to show you my graph. Okay, let's take a look. So I've already gone ahead and made my graph, and you'll notice with this one, I actually didn't make any broken lines here. Why? Because of the side salad that basically looks like it's just lettuce, has 0 grams of fat and 10 milligrams of sodium. So that was almost near the origin, really preventing me from doing that broken line. If you have data that extends all the way down, you got to keep it there. So now I've set my scale to be every 5 grams of fat on the x-axis and every 100 milligrams of sodium on the y-axis. And here's what I can see. Can I draw somewhat of a line through this data? Well, I can draw something that's going to kind of like cut through the middle, just like that. I would still say this looks like it's linear, right? It's not going to be anything that's really curved or anything like that. I wouldn't draw that. I would still say this looks like it's going to be linear, okay? Now the question is it strong? Is it weak? That's kind of hard to tell, right? You know, it's like my line didn't capture anything really. All it did was capture there's about the same amount on either side. Really, actually, our line would probably look something more like this, where we would see about the same amount of dots above the line as we have below the line, right? And so really maybe only one of those lines would, or one or two of those dots would actually sit on the line and the rest would be either above or below. That's probably more what our line of best fit would really look like. And to me, since I have so many that are kind of far away, or it seems like there's something else going on here, I would say this is going to be a moderately strong or maybe even just moderate. I'd say there is a moderate to moderately strong linear, and positive relationship. Between fat and sodium in McDonald's salads. Okay, now we can see that there is something that seems pretty unusual in that side salad that's only 10 milligrams of sodium and 0 grams of fat. But what that does also tell me is that it kind of falls in line with this linear pattern, right? It kind of lies on that line. So it might be something that is considered an outlier because it is unusual. However, it's not something that's so crazy that it's drastically different that it's really going to influence the nature of the relationship. And that's what we call an influential point. An influential point is something that drastically changes the relationship or the nature of that relationship, at least mathematically. Okay, so with this, I would say it's not really an influential point. If I had a salad that was, say, 200 milligrams of sodium and 23 grams of fat, then that's going to drastically change the nature of the relationship. That would bring the strength of this relationship down considerably. But we don't have that. With this side salad that's 10 milligrams sodium and 0 grams of fat, it's not changing the nature of that relationship. It's not changing the strength of our relationship. An influential point is something that will change the strength or direction of our relationship between these two variables. Okay? Now, what we can notice though is there is something else weird that's going on. There is noticeable clustering here. Look at this. They've got these that are grouped together. I've got these three that are clearly grouped together, and I've got these three that are clearly grouped together. Okay? I would say that there are 3 distinct clusters here. That's the most telling thing about this graph. Now, I want to see, is there something that is tying those clusters together? Let's go ahead and take a look at these ones that are highest in fat. Do we notice anything in common between the highest in fat items? They're not only highest in fat, but they're also highest in sodium. So which ones are highest in fat and highest in sodium? That's going to be these 3 salads. What's in common between these 3 salads? Crispy chicken, crispy chicken, crispy chicken. So the math tells us there is some relationship between all of these crispy chicken sandwiches. Okay, and that might seem super obvious to you, but what should be interesting is that the mathematics is pointing us in that direction and telling us, hey, there is a relationship between these. Okay, so the highest in fat and sodium are all crispy chicken salads. What do we notice about these ones? The ones that are low in fat, but they're high in sodium. Okay, going back up, looking at those, which ones are low in fat but high in sodium? That's going to be this one here, maybe also this one, and the very first one. What's in common between all of those? They are all grilled chicken. So the grilled chicken salads were all high in sodium but low in fat. So what do you think is going to be in common between all of these things that are both low in sodium and low in fat? I'm going to kind of guess that they actually don't have any chicken at all. And sure enough, what do we notice? Those without chicken are going to be the ones that are low in sodium and low in fat. Low in sodium and fat had no chicken. And so what's important about this and what you're trying to recognize is that this is, really seems very obvious that, well, of course, crispy chicken is going to be fattier because you fry it, right? You put it in the deep fryer. That's full of oil, which is full of fat and full of sodium. Okay, obvious, right? Same thing though, if and then when you look at the grilled chicken, okay, well it makes sense that grilled chicken would be less in fat because you're not adding in all of that extra fry oil. Okay, and then when you don't include chicken, we know that chicken generally is low in fat, but it is high in sodium. It's generally very salty. So if you have salads that don't have that, obviously that's going to bring the fat content and the sodium content down. But what's important here is to recognize that when there's obvious relationships between things, or maybe you don't necessarily notice it because you're looking at a lot of data, relationships can start to shine through the mathematics here and by looking at the graph. If we didn't look at the graph and we didn't see that clustering and start to like say, huh, that looks interesting, let me investigate that a little bit further, we wouldn't necessarily be able to make that very strong evidence-based conclusion that adding chicken increases sodium and including crispy chicken is going to increase fat. That's the idea that we want to make sure we can recognize. Okay, so there we have it, describing strength, direction, form, and even things that are unusual, including clusters or outliers in our data set. Thanks for watching, you guys. Good luck on your assignment. Have a wonderful day.